We are glad to present our work, URHand, Universal Relightable Hands. Given large-scale light stage data, our model, namely URHand, learn a universal prior for relightable hands. This prior can generalize to novel view, poses, identities, and illuminations. On top of the powerful prior of URHand, we can easily get your hand from URHand. That is quick personalization of a high-fidelity relightable hand from a phone scan. We can photorealistically render it in arbitrary illuminations, views, and poses. Previous work on high-fidelity relightable hands have two limitations. First, it focuses on identity-specific reconstruction, which cannot generalize to novel identities. Their architecture is designed for single identity fitting, which may not fit for cross-identity generalizable learning. Secondly, they require two-stage training, where teacher model is trained on OLAT sequence and student model learns to match with the appearance generated by teacher model under natural illuminations. This two-stage training requires lots of environment maps to synthesize data for each identity, which is not scalable with large-scale cross-identity data. Therefore, for a high-fidelity universal prior of relightable hands, we have three major challenges. First, scaling the cross-identity training within a unified model. Secondly, how to maintain the personalized fidelity and sharp details. Thirdly, how to achieve generalization to natural illuminations without teacher-student distillation, making the large-scale training tractable. To this end, we propose our learning framework URHand. It takes as input the coarse tracked mesh, hand pose, and mean texture. Our model consists of two parallel branch, or just the physical branch and the neural branch. The physical branch focuses on geometry refinement to get personalized details and providing accurate shading features for the neural branch. Specifically, we feed mean texture and hand pose to a UNet, which predicts displacement map and roughness in the UV space. The coarse mesh is unwrapped into UV space to get coarse normal map. The displacement map refines the coarse geometry accordingly and yields the refined normal map. Given lighting, view, predicted roughness, and refined normal, we leverages a physical BRDF to compute diffuse and specular feature as well as the physically based rendering. The physical branch is supervised by image reconstruction loss against ground truth. At the core of neural branch is the linear lighting model. By removing nonlinear activations and bias in the neural network, the linear net explicitly keeps the linearity of output with respect to the input. We feed the physics-inspired shading feature into the linear net, thus the linearity of light transport is satisfied. It guarantees our model can train on OLAT sequence and generalize to arbitrary illuminations without additional training. The nonlinear dependency like pose and identity is incorporated by a nonlinear net. We modulate the linear net using the features from nonlinear without breaking the linearity. The linear lighting model predicts gain and bias map which contribute to the final rendering. The neural branch is supervised by reconstruction, adversarial, and regularization loss against ground truth. Here are the qualitative comparisons with state-of-the-art methods for relightable hands under directional point light. Our method, URHand, clearly present best possible high-fidelity rendering with realistic shadows and specularity. The baseline with physical-only rendering fails to achieve high quality, which highlights the importance of the joint learning of physical geometry refinement and neural rendering. Next, we show the impact of different physics-inspired shading features as input to the linear lighting model. Only the full model can produce high-quality rendering, specular highlights, detailed geometry, and correct shadows. We also compare alternative designs of our linear lighting model for neural rendering. When generalizing to environment maps, nonlinear model cannot render in high quality, and MLP-based linear model cannot produce pose-dependent shadows. Lastly, we present more results of our high-quality rendering across identities, poses, and illuminations. Our relighting with directional point light shows fine-grained details and specular highlight on skins. Thanks to our linear lighting model, URHand generalized to environment map lighting within one model and no additional training. On top of the prior of URHand, we achieve quick personalization of a relightable hand from phone scan. Now you can relight your hand in high quality with URHand and bring your favorite nail polish to your avatar. Thanks for your attention.